Hello, everybody. Today, we're going to talk about derivatives using implicit differentiation. So let's just get right into it. What I want to do is work on a few examples where one would use implicit differentiation. So let's say we have the following equation, and the mission is to find dy dx. All right, so that's our mission. Find dy dx given the above equation. So, to do implicit differentiation, that denominator is going to play a huge role. Because what we're going to do, and what I'm imagining, is this item right here will be apply the derivative with respect to dx on both sides. We're going to take the derivative with respect to dx on both sides, because that's really what implicit differentiation is. So how does one do that? Well, again, it's all about the last outside operation, which is the log. So I'm going to take the derivative on the left-hand side, dx, with the log. Well, the derivative of the log is the derivative of the inside over the inside. But there is an issue. So this is the inside. That's your u. Remember, the derivative of the log is u prime over u. The problem is xy. Whenever I need to take the derivative of this, which is up here in the numerator when I do it, right? Because that'll be the derivative of this would go up here. When I take the derivative of this, that's a product rule, people. Recall, whenever you have back-to-back letters inside of an implicit derivative, you're going to need the product rule. So this is a very complicated one. And again, what I always tell you guys is to pause it to make sure everything makes sense. Pause it, do it with me, try it out. The right-hand side, no big deal. The derivative of x is 1. And I check out the denominator letter with respect to dx. X matches, so no needed for a multiplier by the chain rule. The derivative of 2 is 0. All right, let's go to the right-hand side. Sorry, back to the left-hand side. What we have over here is we have the product rule. Why? Because, again, what is the derivative of a log? It's the derivative of the inside over the inside. So there's the inside. The derivative of the inside, forget the derivative of 1, that's 0. The derivative of xy, that's the critical piece. The derivative of xy, which I'm about to do here, is got to be a product rule because x and y are functions. So it's u prime v, so that's a y, plus u v prime. All right, so let's try this out. The derivative of x should be 1. And in fact, it is just 1 because x matches the derivative with respect to. The derivative of y is 1, but there's the rub. The derivative of y will be dy dx because we do not know what y is in terms of x, so we need that extra dy dx. Because again, at this moment, you're taking the derivative of y. The derivative of y should be 1, but that's y, not the x that we're taking the derivative with respect to. All right, so we have done the derivative d dx, as we call this, the derivative with respect to x on both sides. All right, so if you notice, there's only one dy dx. The rest of this question is to get that dy dx all by itself, and then that goes in this box right here. The rest of this question is just algebra. What type of algebra is needed to get that green by itself? Well, we got to go back to our 5th through 8th grade algebra. If I'm solving for this, first thing I'm going to do is cross multiply. Multiply this denominator over. Second thing I'm doing is cleaning up. Y times 1 is y. X times dy dx is x times dy dx. Cross multiply, I get xy minus 1 on the right-hand side. So I cross multiplied and cleaned up. Again, I multiply this over. Y times 1 is y. X times blah is x times dy dx. All right, subtract the y over, because that's good algebra. You're going to get xy minus 1 minus y. Because you cannot combine, there are no like terms. Subtract the y over. Those are, nothing here is like terms, because this is an xy, this is just a y. Last but not least, my dy dx, and many of the times when you're doing implicit derivatives, the derivative is not going to be the prettiest when you're finally done. The dy dx, when you divide the x over, because that's what I'm going to do, get rid of a times, right guys? Hello guys. So we've just completed this example. So what I would like to do is move on to another example. Allow me to skip over some of my scratch work I was doing earlier. And let us continue on with our path of taking derivatives using implicit differentiation. Of course, you only do this when needed, right? You do implicit differentiation as needed. So when does one need implicit differentiation? When you get an equation where solving for y or x may not be the easiest to do. You may not be able to get y equals. That would be explicit. If I can solve for y equals, we should do that. But if we can't, if it's better just to leave it in its implicit form like you see here, then sometimes it's okay to leave it this way, but we still want to know about rates of changes. For example, this example. What we have here is we have the sales volume, Y. So Y is the sales volume. And we have X, advertising money. X would be the advertising money. And I would love to know how they relate to each other. That is, how much money we spend on advertising relate to how much sales volume changes? And in fact, that's my question. What is the change in sales volume as we increase or decrease the change in money? So if I had more $1 million or a dollar, depending on the roots of units here, that is, I have to know the units, money. Is this in millions? So if I add another million to my advertising budget, what does it do to the sales? If this money's in thousands, if I add another 1,000 to advertising, what is it going to do to the sales? Again, I like to look at really practical examples, and you can't get more practical than this. We have an equation that relates advertising budget or advertising money to sales volume. And I'd love to know, again, if I add more money, an extra 1,000, an extra million, whatever the units are, how will it change sales? And that's what this derivative does. It tells me the rate of change of volume with respect to the change in the money, the advertising budget. So I want this derivative dy dx. All right, to take this derivative, no big deal. We do it implicitly. So that means we do d dx of both sides. So if I take the d dx of the left side, be careful. Whenever you have back-to-back letters, you know you're going to need the product rule. So when I see the xy, I automatically know it's product rule time. Anytime I have back-to-back letters, I need a product rule. So the derivative of xy is a product rule. The derivative of 20x, no big deal. The derivative of 20x is a negative 20. Keep track of your signs. The derivative of 10y, got to be careful there. The bottom letter x. The derivative of 10y will be 10 dy dx, and the derivative of the other side is 0. All right. Again, the derivative of the bottom letter is a clean derivative. The derivative of the top letter is the one where the chain rule applies. You need the dy dx. Keep practicing your implicits. All right, derivative of the product rule. Derivative of the product rule is u prime v plus u v prime. So the derivative of x is 1, that goes there. Derivative of y is 1, but once again, it's 1 dy dx. For the same reason, I have a dy dx there. Again, what one should do is before they check out my work, you check out my work, you have the example, right? You know what I want. Change of volume with respect to sales. Let's try this again. This would be the rate of change of sales with respect to money. Let's make that very clear how the question would be asked. Find the rate of change of sales with respect to money. Adding money to the advertising budget. What is the change in sales with respect to the advertising budget? You got to know your letters. In this case, that would be dy dx. All right, so try it, and you get this. Clean it up. Sure, 1 times y is 1y. X times dy dx is x times dy dx minus 20 equals 10 times dy dx. There's no equals. I do apologize. That would be a plus. That's me getting lost in my work. So that should be a plus. And then there is an equal 0. So as I've done in previous videos, keep the terms with dy dx on one side. Move the terms that don't have a dy dx to the other side, called good algebra. Get rid of the 20 by adding it. Get rid of the y by subtracting it. Notice the terms on the left hand only have a dy dx now, so I can factor that out because that's my usual steps of solving implicits. And then the last step, as you know, divide over the parentheses. And so my dy dx is 20 minus y over x plus 10. And there we have it. I have the rate of change. I know how sales will change with respect to the advertising budget. All I need now is a particular time and moment of your company. You tell me a particular X and Y, and I'll plug it in to let you know how things are changing. So if we are at the point, let's say we're at the point, of course, I got to make sure I pick a point that's on this curve. Like say X is 10. So if X is 10, the first thing I got to do is go up top and make sure I pick a number that makes sense. When X is 10, what would Y be? You always got to go and check your math. It's got to fit on the equation. You can't just willy-nilly pick a point, 10, 2, 10, 4. That doesn't work like that. You got to plug in 10 for X, all right, and solve. When I plug in 10 for X, that makes that 200. Put 200 over there. I get a 10 there. I get 10y, and 10y make 20y. 20y equals 200. 20y equals 200 means y equals 10 also. That's kind of funny. So we should have the point 10, 10 on this curve. I plug in 10 in for x and y. So let's try it. 10 times 10 is 100. 10 times 10 is 100. 10 in here is 200, so that all wipes out and makes 0. So 10, 10 is a point on the curve. You should really pause right now and figure out how I got the y value, all right, 10. All right, so if the point is 10, 10, then we can plug in and find dy dx. Your dy dx, when you plug in 10, 10, would be 10 over 20, or 1 out of 2. So that tells me if we add, so what I can explain now is if we add 1 unit to advertising, then our sales goes up by a half unit. Or another way to put it, for every $2 you put into advertising, you get an extra unit of sales. That's the other way to put it. If we put an extra 2 units of advertising, whatever the 2 units are, $2,000, then our sales goes up 1 extra unit or an extra 1,000 in units. It all depends on, I have to say it in this case, what are the units? Are we talking about thousands, millions? You got to be careful. What I know is if we add 1 unit to advertising budget, then our sales will go up by half a unit. So it's a 1 to a half ratio or a 2 to 1 ratio. That is, for every $2 you put in the advertising budget, you get an extra unit out, an increase in your sales volume. Again, I love understanding the derivative when it comes to a practical problem. And there's nothing more practical in marketing or in management than dealing with sales volume. And what happens if you can bargain to your boss for an extra revenue source, an extra money for your advertising budget? What will the change be? Can you sell that boss on that change? And doing all this work, this is what you can say is, hey boss, for every extra $2 you give me, I can get us an extra unit in sales. And that's good information to have. All right, one last problem. So again, today's videos are all about utilizing implicit derivatives in applications. How do you know you have an implicit derivative? That just comes down to practice and training. If you know it's not easy to solve for y, then it's most likely an implicit derivative. Like this example I'm writing down. Solving for y may not be a very convenient thing to do, but I still want the derivative because it gives me a change, a measure of change. So here's my equation. The first thing I do with every equation, and let me read this, 300x plus 30,000y equals 11xy, by the way, 11xy minus 0.002x squared minus 5y. So taking the time to solve for y may not be beneficial for me. So now, what does this equation do? That's the next thing I like to make sure, is I know what each of these do. So what we have is labor hours x So X is labor hours. Got it. And for our labor hours, what kind of product are we looking for? And the answer would be for Y would be acres of a crop. So we're looking at farming. You know, for a certain amount of labor hours, you get a certain amount of acres of a crop cultivated. So that's good to know. You know, for farmers that are out there with millions of acres of crop, how long is it going to take? How many labor hours? How labor intensive is it? If this is the equation, it's nice to have this. And it would be nice to know, you know, what happens if we buy out a company and we end up with more acres? What would be that change? You know, what would be the rate of change of labor with respect to acres? And I know I'm spelling that poorly there. Acres. Rate of change of labor with respect to acres. Because if we sold acres, and so that means we decrease the number of acres, what does that mean for rate of change of labors? If we increase acres of a crop, maybe per season, there's a lot of reasons you would increase and decrease the acreage of a crop. And we'd love to know how much influence does that have on your labor hours. So what we're looking for, let me make sure I got my letters correct. Labor is X. So rate of change of labor, dx, with respect to acres, dy. So that's the first thing. You should pause and make sure that makes sense to you, that I'm looking for dx, dy. And the reason being is because labor is X, and with respect to acres is Y. Whatever follows with respect to is typically your denominator with respect to your denominator variable. And that's the most important variable, to be honest. Because I know I'm going to do, and let's be careful here, d dy. Please notice that now. I'm doing something different, and that's why I wanted this example to be done. I'm doing d dy. Nothing wrong with that. I don't care. I can do whatever letter you want. I just got to be careful. 300x. Well, let's take some derivatives. Derivative of 300x should be 300, but that was an x, not a y. That's why the dx dy. Derivative of 30,000y is 30,000, and so I'm going to leave it as 30,000. And that's a y, and the bottom letter is y, and so it matches. So the left-hand side is done. The right-hand side, here we go, my friends. Back-to-back letters is a product rule. One more time. Whenever I have back-to-back letters, I know I have to do a product rule. So I'll leave that there. What else do I have here? I have this. Well, 0.002x squared should be 0.0004x. So it should be minus 0.0004x. But that's an x, not a y. So that's why the chain rule. The derivative of 5y is 5 because the y matches the bottom letter. It's always about that bottom letter to know which one gets the additive piece or not. And I shouldn't say additive piece, the multiplicative piece, the chain rule. Should be very clear in my words. All right, 11x is u. So if you do u prime v plus u, and y would be v. All right, so now I'll stop scrolling up and down, driving you guys nuts. Again, how do I know it's a product rule? 11xy, x times y. X and y are producted, and that's why I need a product rule. Back-to-back letters will always be a product rule. So how does one do the product rule? See my previous video on product rule. The derivative of 11x should be 11, but that's an x, not a y. The derivative of y should be 1, and it is 1. And the y matches the denominator with respect to. The with respect to variable is key, and that's how I took the derivative here carefully. Now, we need to clean this up. So, what do we have here? 300 dx dy. Allow me to write that as x prime to really keep it simple in writing. Plus 30,000 equals y x prime, because it's y times dx dy, plus 11x minus 0.0004x, x prime minus 5. Try to get everything on one line here so we can take a look at this. And then I'm going to highlight the items with the x primes. Those are the terms I'm going to be moving to one side. Those terms have to go one side. The terms with the non-primes have to go to another side. So I'm going to move the green to the left the red to the right. This is all about algebra now, guys. So the green to the left. So I have 300x prime minus yx prime plus 0.0004x dot x prime equals, move the green to the right. So the only thing I got to move over is that 30,000. So I get 11x minus 30,005, because the 30,005 can be combined because they're like terms. Excellent. Now everything on the left has an x prime, that is its dx dy as we shorthanded it. When I factor it out, I get 300 minus y plus 0.0004x, and that'll equal 11x minus 30,005. From this point, we're done. We divide over that expression, and here we have it. We have the rate of change of labor hours as it deals with the increase or decrease of acreage. It is a very complicated equation, and what I would need now is a particular point in time. You give me a particular point in time, and I would determine what's going to happen. In general, what I have is I have right here this equation that I just found is, this is the, if we increase acreage by 1 unit, then dx dy is the change in labor hours. In general, that's what this equation tells me, is if I increase, all right, if I increase the acreage, which is the y, if I increase the acreage by 1 unit, so 1 acre, this function right here, and it's not really a function, this equation, will tell me if or what will happen to the change in labor hours. That's really what it'll tell me. That's really what the derivative tells me again, is this tells me if we increase acreage, because that's what y is acreage, by 1 unit, this whole thing, this whole fraction tells me what's going to happen to the change in labor hours. Again, a great example of how the derivative can really help us in a management type of situation. Again, labor hours. That's a very important topic in management, is how many labor hours do we need? And so having this equation right here, this equation right here, that's a beautiful equation. What it tells me is if you give me a particular x and y, you give me the particularly how much you're spending on labor hours and how much acreage you have currently, right? Because that's what x and y are. Current number of labor hours, y is current number acreage. You tell me that. Plug them in. I'll tell you what's going to happen if we increase in acreage, how it will change the overall labor hours. It's really good to have a projection, a forecasting. I thank you guys for watching this video. Please stay tuned for other future videos.